before we build the full op-amp using the folded cascode structure, let us quickly look at the gain and noise performance of the simple single-ended folded cascode structure. So we will assume that the input is an NMOS and the cascode is a PMOS device. Now we need to do something about the output node. Now earlier we had looked, for simplicity's case, we had assumed that the output is resistively loaded, but it normally doesn't make sense because the minute you have a resistive load, you really don't need the large output impedance that this particular structure offers, right? So you really want to get higher DC gain from this structure. So naturally you ideally want to use an ideal current source so that you will get the gain of maximum, you will get the advantage of maximum gain from this particular op-amp. Now how do you make a current source? You of course cannot make ideal current sources in practice. So the first thing you try to do is to try to replace that with a transistor. So please note that the output impedance of this, so maybe I'll call that R up is something we need to write down. So before we move on to the replacing the current source, because this is going to become significant in a few minutes. So what is the expression for R up? So as you can see, the gate of M2 is connected to a constant voltage, and therefore M2 is a common gate structure. You know that any impedance at the source of the common gate structure is multiplied up by the intrinsic gain of the common gate transistor. So therefore you expect the impedance to be GM2 RDS2 times Rx, if this node was node X, times Rx, and this is GM2 RDS2 times Rx is of course the parallel combination of RDS1 parallel RDS0. So this is the impedance looking upwards at the drain of M2. So this is of course quite high. We now want to use an ideal current source here, but we know we can't do that. So let us first try to replace that with transistor, with an NMOS transistor, because this is a current flowing downwards. So the first thing we'll try to do is to replace it with some VB at its gate such that this has some current. Now clearly this NMOS transistor will now have some resistance, let's say let me call this M3. This will have some resistance RDS3, and therefore R down will be equal to RDS3, and the total resistance at the output, which is the output resistance RO, is R up parallel R down, and this is clearly the parallel combination of GM2 RDS2 into RDS1 parallel RDS0 in parallel with RDS3. And now you can see that the impedance looking upwards is of the order of GM-RDS squared. It's slightly lower than GM-RDS squared, whereas the impedance looking downwards is of the order of RDS. It is going to be very difficult to make these of the same order, and typically what you'll find is that R down in such a case will always be much smaller compared to R up. This is not the best case because you wanted a current source which would have a much higher impedance compared to the impedance looking upwards, which will give you the maximum gain from this particular stage. So now it becomes clear to us that you need a better current source at the bottom. So now if you want a better current source, you of course have to use a cascode structure even at the bottom. This will give you an even better output resistance. So let me call these transistors M3 and M4 with gate voltages VB3 and VB4. Now if you use this current source, R down will be equal to GM3 RDS3 times RDS4, and therefore your overall output resistance, which is R up parallel R down, will become equal to GM2 RDS2 times RDS1 parallel RDS0 in parallel with GM3 RDS3 times RDS4. Now as you can see, this is somewhat close to that of the telescopic cascode, but you just note that because of this particular term here, this gain would be slightly smaller, and in general gain and R out of the folded cascode so will be around 2-3 times smaller than the telescopic version. Which is the regular cascode circuit. So in general, when you try to decide all of these RDS values, you will find that it's a little bit lower than that of the regular cascode, but it is still much higher than that of the regular one-stage op-amp, the simple common source structure. But so this is the template that we are going to use for our analysis. So this is the 5 transistor structure for the folded cascode, single stage folded cascode, single-ended folded cascode. So now we can write the expression for the gain. So let us assume that a voltage V in is applied to the gate of M1. Clearly that should also include some bias voltage VB1. The bias voltage at a gate of M0 should be VB0. Now let us look at what will happen when you apply a signal. I am not going to draw the small signal structure because we are now at a point where we should be able to visualize the small signal structure of each circuit and of slightly more complicated circuits. So when I apply this V in between the gate source of M1, you will have a current I1 flowing through M1. I1 should clearly be GM1 times V in. And this I1 has 2 paths to flow. The first path is through transistor M0. The second path is through transistor M2. And of course with the opposite direction, since I have already chosen the directions. So these will be the 2 directions of I1. So I1 should be equal to I0 plus I2. And this is purely from KCL at node X. Now part of this current will of course flow through M0. Ideally you want to design the circuit such that as much of I1 flows into M2 as possible. What is the impedance of this circuit looking downwards at the source of M2? Please note that the impedance at the drain of M2 is quite large. So you cannot assume that the input impedance at the source of M2 is equal to 1 over GM. So this particular assumption is not valid because you have actually connected a very large resistance at the drain of M2. So please note that. So the current will split in some form depending on the two impedances. Now this current will now flow through the output node at V0. The total output impedance is given by R out, and therefore that will give you a certain amount of gain. So this will give you the small signal gain. So let us assume that we design M0 such that it has much higher impedance compared to the output impedance of RDS of M1 and the input impedance at the source of M2. So I am going to call that RS2 so that we'll distinguish it. So we will assume that RS2 is designed to be smaller, let us say much smaller than RDS1 and RDS0. So there are three paths for the current to flow at node X. One of them is the output impedance of transistor M1. The other is the output impedance of transistor M0, and the third path is through the source of M2 itself. So we will assume this is true, and therefore the small signal gain we now assume that all of I1, the circuit has been designed such that all of I1 flows through M2. So the small signal gain now is minus I1 times R out times R out. Sorry, this is the output voltage is minus I1 times R out. So this is minus GM1 R out times V in. So VO by V in, which is the small signal gain of the circuit, which is minus GM times R out. So this is minus GM times, as we have seen, R out is GM2 RDS2 into RDS1 parallel RDS0 in parallel with GM3 RDS3 RDS4. So this is the expression for the small signal gain of this particular folded cascode structure, and this will give you a slightly lesser gain compared to the regular cascode, but this is still larger than the simple common source structure that you would have seen before. So now let us look at the noise performance of this particular cascode structure. So let us first make a copy of this particular amplifier so that we can now analyze it for noise. So, as always, when you analyze for noise, the first steps are to apply the appropriate voltage and current conditions in the circuit. So clearly, when you are analyzing for noise, that you assume there is no input signal because the noise is uncorrelated with the signal. So therefore, there is no input signal, and since noise is a small signal quantity, you assume that small signal equivalent circuits are valid. And therefore the bias voltages at the appropriate nodes will be grounded. And so far so good. So now this structure, you find that there are actually 5 sources of noise in this circuit, and the 5 sources of noise are the drain current noise IN1 of M1, IN0 of M2, IN0 squared of M0, IN2 squared of M2, IN3 squared of M3 and IN4 squared of M4. So there are clearly 5 different sources of noise in this particular circuit. Now let us look at each one of these and figure out if that noise will make its way to the output. The easiest way we have seen earlier is to short the output to ground and then look at the output short circuit noise current. So in short circuit condition, we are going to look at the output noise. We will of course assume that the noise of each transistor is uncorrelated with each other. And now we need to find out the mean squared sum at the output node. Let us start going through each of these one by one. So this is noise analysis. So if you look at noise of M1, so you will find that the noise of M1, when you do this noise of M1, we will assume that the other noise sources do not exist, and this noise of M1 flows between the drain and source of M1. So at node X, this current has 3 parts or 3 ways to split. It can split just like your small signal. It can split through RDS1, it can split through RDS0, and it can split through the source resistance seen, the resistance seen looking into the source of M2. As we have seen earlier, just right here, we have assumed that RS2 is much smaller than RDS1 and RDS0, so that most of the current flows through M2 to the output. And clearly, since we have designed a circuit such that that happens for the signal, you should expect that all of INs 1 squared appears at the output. So the first component of IN out squared, which is IN out 1 squared, is equal to IN 1 squared. So pretty much all of noise of M1 will appear at the output short circuit. What about M2? If you look at noise from M2, so if you look at the noise of M2, that is again a current source which is across the drain source of noise of M0. It is across the drain source of M0. And as you can see purely from the circuit topology, this looks, IN0 looks exactly the same as IN1 squared, purely from a circuit topology. You should expect that IN0 squared also has 3 paths to flow through. The first one is through RDS1, the second one is through RDS0, and the third path is the impedance looking in at the source of M2. So therefore, you should expect that IN out 2 squared should be equal to, IN out 0 squared should be equal to IN0 squared. This is the second component of noise. What about M2? Noise from M2. So M2, remember, is the common gate structure. Normally, you do not expect additional noise from M2 because, as you might expect, the noise from the cascode does not make its way to the output. Let us confirm that this is indeed true by doing the following. So let us consider the noise from M2. Now, we do not know how to analyze this really well. When the current source is connected across 2 nodes of the circuit, so we'll go back to the trick that we have studied earlier. We will now split this into 2 correlated current sources. So just to remind you, I will now show that I will now point out that if you have a current source I between 2 nodes 1 and 2, As far as the rest of the network is concerned, this is exactly the same as putting two current sources in series, because the rest of the network assumes that a current I is pulled out of node 1 and pushed into node 2, and KCL is clearly valid even at the intermediate node. And this is again not changed if I were to connect this to any convenient voltage, because there will be no current through this particular branch, and I will connect it conveniently to ground. So now how does this affect us? I can now replace this with a pair of current sources. Like this, each of value I and 2, and I'll connect this conveniently to ground. So now this makes our job much easier, because now I can consider these two current sources. The only thing I have to keep in mind are that these two currents are correlated noise current sources. So therefore, I cannot work with mean squared values. I have to work with the root mean squared values and keep track of the sign. So now let me use two different colors to distinguish between these two guys. So let me use red and blue. If you look at noise current IN2, I expect that to behave exactly the same as noise current of M0 and M1. I expect all of that current to go through M2 into the output short circuit. And this should be clear, because looking in at the source of M2, I have a short circuit at the drain of M2, and therefore looking in impedance at the source of M2 here would be 1 over GM in this case, in the case of noise analysis, and that is clearly much smaller than RDS0 and RDS1. And so clearly noise of all of IN2 in blue color will flow into the output short circuit. So the component, so IN out 2, I am still following the root mean squared value, will have a component being pulled out, and I am going to call that IN21, and that is being pulled out. What about the red color current source? So that current source has two paths to travel. One is looking up at the drain of M2. The other is through the short circuit. Clearly this current is again going to flow through this, and so maybe I can just use directly IN out 2 is going to be equal to minus IN2 plus IN2. These are the directions of the two current sources in blue and red. As you can see, these two current sources are equal and opposite, and therefore this current is going to be 0. As you can see, there is clearly no noise generated from M2 at the output. And therefore, this we have seen before even for the regular cascode. When we analyze the noise for the telescopic op-amp, you do not expect noise from the common gate structure, especially at low frequencies. What about M3? Transistor M3 is again a common gate structure. You do not expect any noise at the output. You can follow the exact same procedure and show that the output noise generated by M3 is 0. And M4, of course, will generate noise. All of this noise will flow through the output. So therefore, the total output short circuit noise, which I'll call by IN out squared, is going to be IN out 0 squared plus IN out 1 squared plus IN out 2 squared. Remember, I have 5 noise sources. I need to calculate the effective short circuit current and add the root mean squared value for all 5 of them. So these are the 5 components. We have already established that noise from M2 and M3 are 0. So these two are 0. And therefore, for the cascode, you have 3 sources of noise. So this is IN 0 squared plus IN 1 squared plus IN 4 squared. I apologize. So there are 3 sources of noise. This is the short circuit noise. The input referred noise voltage, which I will now represent as EN squared, is nothing but the short circuit noise over the overall effective transconductance squared. The effective transconductance of this circuit is, of course, GM1. I will write that down here. That is the GM effective transconductance of the overall amplifier. So therefore, the input referred noise is going to be IN 0 squared plus IN 1 squared plus IN 4 squared over GM 1 squared. And what is IN 0? That's clearly 8 kT by 3 GM0, and let us say that I am interested in the spectral density, and remember, I am looking only at thermal noise. I can always add the flicker noise component to this as and when required. So this is clearly 8 kT by 3 into GM0 plus GM1 plus GM4 over GM1 squared. So of course, now similar to the cascode, you can see that you can look at the conditions that you would need to get a truly low noise solution. You clearly need to maximize the value of GM1 and minimize the relative values of GM0 and GM4. So clearly the GM of transistor 1 should be maximized. The GMs of this transistor and this transistor M0 and M4 should be minimized for you to achieve very low input referred noise. Now we are in a position to build the folded cascode op-amp and write down directly its noise expressions and gain expressions and so on. That is what we will do in the next lecture.